So today I will cover the particle tracking method. So this is the second session. So here just a very brief one page summarize what we did yesterday for the subset-based tracking. So you just track those subsets. So for your experiments, just some key summaries. You need to paint some patterns, black, white, 50%, 50%. Each speckle dot is 3 to 5 pixels. So when you do the post-processing, the subset size about 3 to 8 speckle dots, and also the subset spacing about 25% or 100% of the subset size. And there are lots of the useful resources you can always look into the IDIC Society website. There's also a very nice guidebook. And finally, what you get is just what you're always solving is the displaced field and the strain fields. And so imagine if you also know the materials model, right? So you can plug in the materials property, then you also know the stress field. So this is yesterday what we did. All these useful links, code websites, I also put in the box folder. There is a document called the links. So if you miss the yesterday's session, it's okay. Just all these resources will be available and open source to you. And yesterday, I forgot to mention the many people use our codes. And also we have very nice collaborators. So I want to thank them. Okay, so today we will move from the continuous tracking. Continuous tracking, you can imagine, is based on the subset or local window. So for the image tracking, the window to window. So now we are doing the discrete. Discrete means there's some discrete, some local points or some fluorescent beads. So the tracking is also just a bead to bead. So it's also called, if you just track individual bead, it's also called a single particle tracking. If you track all of them, people also call them multiple particle tracking. The tracking also gives you the same thing, the deformation field, which means the displaced field and the strain field. So their goal is the same, just that they work for different pattern, different experimental condition, and other things. So today, I will have more for the code demo in the third and fourth. They will be combined together. So before that, just a quick to give you some basic idea of what's particle tracking and where you can apply them, and what's the comparison between the particle tracking and the subset-based DIC and DVC. So when you should use the particle tracking, or when you should use the DIC DVC. Also, just a very quick experimental guide for how to design the experiments. So because the particle tracking, so this method just what is called, so just to track those particles. So these particles, they can be 2D particles, so you track the 2D deformation. So for example, here those flow, to track particles, you get the flow field, you get the velocity field, the vorticity field, you have lots of those information. In the 3D, so you can track those 3D fluorescent beads. You can track how the deformation between the cells and the substrate, right? So if you also know the property of the substrate, so you can also measure the force between the cells and the substrates. So besides this idea, it can be applied to many disciplines, right? So for example, you can to measure the fluid flow, like this is the flow in the lung, based on experimental data sets. And you can also measure like what we did either for the solid materials. So there's the foam with lots of those dot patterns, and we can track those dots, so we know the deformation of the foam. Right? And so similarly, you can put it in the soft tissue or soft gels, you track their deformations. And besides the solids, in material science, you can also put in the colloids or granular mechanics, or you can put in the biology, you can track those cells deformation. Or for the computer vision, you can measure how people are walking, and also what's the traffic flow. Also, you can count how the penguin they are moving. So just to give you some idea, the baseline scale can be quite small, like the scale of the cell or atom, or can be quite large, like those animals or cars or like planets. So the thing just you have something to track. Yeah, here's another example, that's the atom. So this is from the images from the transition electron microscope images. So you track how these atoms they are moving and what's the phase transformation in the materials. So you see there are lots of applications, right? So either to measure the deformation field, right? And we also know that DIC DVC is also to use to measure deformation field, right? So how the particle tracking compared with the DIC DVC? So when should we choose the particle tracking? So the advantage of the particle tracking is, so if you remember yesterday for the subset, there is the size limit for the selection of the subset size. The subset size cannot be too small. And sometimes if you have volumetric images, right? So the number of these stacks cannot be too small, because if the number of these stacks is too small, you cannot define there is a window there, right? But for the particle tracking, there's no such geometry limit. You can always to track single particles. So it still works for some low resolution or bad particles patterns. And also for the deformation, in the subset of DIC, you always track subsets. So you assume each subset has the same uniform shape function for the deformation. Right? So you just track them the whole area of each local subset. For the particle, you just track for each individual particle. So you can use this to track more like oscillating or turbulent deformation fields. And also a subset that you track the subsets, for which is each pixel will count. For the particle, you just track those centroid of the particle, so that the cost is much cheaper. Also, similarly, DIC DVC, you need some mesh and where the nodal points would track, right? For the particle tracking, you don't need such mesh. So there are lots of can be easily naturally combined with lots of those mesh-free, like a material point method or other method, can handle very complex geometry. But there's also some disadvantage with the particle tracking. So if your experiment is okay to paint those DIC patterns and to do DIC experiments, usually DIC has a better accuracy than the particle tracking. But sometimes it's harder to paint those particles because of environmental or experimental conditions. For those cases, particle tracking still gives you something. And also for particles, you need to accurately and robust to detect the center of the particle. Sometimes this can be hard because under the microscope, some particles, they may not be spherical. They may have very complex like lightning or some lots of those like environmental effects. So this will influence the accuracy of the particle tracking. And also particle tracking, because you just track the individual particles. So there may be some local outliers. For example, the mismatch, or maybe just a few particles, their centroid not accurate. So for those outliers, particle tracking is harder to remove those bad points. And also particle tracking is less robust, and the solution can be not unique, because the solution just a one-to-one. You can see the solution is not unique. It's not as robust as the DIC DVC. Okay, so there's a comparison between DIC DVC and particle tracking. It really depends on what's your experimental goal and what's the experimental condition, and you need to choose what's the method, like which one to apply. So for the practical guide for the experiments, so it's almost the same with the yesterday DIC DVC. Because all this definition, you put on the if you also type it, you have some loading system and the specimen with under some definition. You use the high-speed camera to capture the images, and then you use some software or code to do the post-processing and to refer what's the definition of the images, and then use those definition image to tell what's the definition of the specimen. So all this setup is the same as before. You need to have a very nice, robust, aligned loading system. So, and your images should be clear. You should not be blurred. And also, so here just a quick, all the same with yesterday's topic. Also particles, they should have some high contrast to detect their particles. The particle need to have some non-repetitive distribution, so you can know, you can better to define the particle point feature to distinguish the individual particle with other particles. And the particle, just in the ideal case, they should not be overlapped. Otherwise, you need some additional care, like a watershed algorithm or other algorithm to deal with those overlap particles. Also, particles, they should be just very nice, closely to contact to the surface of the specimen. they should not just leave the specimen during the deformation. So otherwise, the deformation particle cannot tell you what's the definition of the specimen. Also, to print those pattern for the particle tracking, you need those dot-like patterns. There are many methods. You can use a stamp, or you use some additional particles like some painting ink something, or like a 3D print those particles. So all this like a roller, stamp, microfiber, or like what we mentioned yesterday, use the 3D printer can easily to paint those dot-like patterns. And then you can just use some software to detect the particle and track it. And also same as before, you need to have the very nice lighting condition so your image is clear and there's no shadow effects. Here the same for your camera, you should not have the autofocus or other effects to change the image quality. And then you just put in the software code. So we will focus more on the code part today. So similarly, for the 3D particle, you need some, for example, in the biology experiment, right? You put some fluorescent beads that's ideal, some particles. So for your imaging, each particle, you should have some size. So for example, the diameter should be between 3 to 5 voxels. Because if your diameter is so small, just like less than 1 voxel, it's the detection of the particle may be inaccurate for their centroid position. So your particle should have some size so you can better detect what's the centroid for the individual particle. So, but if the particle is too large, you may lose some spatial resolution. So this is just some empirical value. And also for the particle, if it's too sparse, like the CD density, if it's just too low, you may not have many particles there, right? So you also lose the measurement spatial resolution. But if you have too many particles, so because the lightning effects, their image maybe particle will be overlapped, right? So there's some issues there too. So finally, your images should be like something like here what I showed. This is from experimental images. You have some particle in the images. They are not overlapped. They are not too dense, but they're not too sparse. You can use this particle to measure the deformation. And then you should have some, at least even you have just one single layer particle, right? You should at least have 3 to 5 voxels to better find what's the centroid for each individual particle. So yeah, please pay attention to this when you design or scan your images. So before I show the code and for the post-processing part, there's some questions for the first 2 parts. If the question just speak out, if no, we'll just move to the next part. Okay, so we'll move to the next part. So here, because yesterday we may go too fast and there's no time to show how we use the code. So today I will just combine to demo the code and tell you what's the method together. So basically for the post-processing of the particle tracking, there are 3 parts. First part is to particle detection to detect where the centroid of each particle. And after that, you just to match or link each particle to find like which one goes to where. And the movement of the centroid of each particle means it's a displacement. And after solving all this particle matching or linking, you can further use the soft displacement field to compute lots of things like the velocity, strain fields. So there's some other post-processing step there. So the most difficult and important one is the particle detection, the particle matching or linking. So after finishing these 2 parts, all the other stuff quite straightforward. So the particle detection, there are many methods here. You can use like for example, you can find some where the highest intensity for the particle center, or some feature detection, or some machine learning method, the functional methods there. So today I will demo you 2 simple, straightforward methods. One is called use the Laplacian of Gaussian filter to define the feature of each particle and find the central of the particle. And the second one is we use the point spread function to do the deconvolution to get to the central of the particle. So the first one is the Laplacian of Gaussian. That's what LOG means. The Laplacian of Gaussian is just one function. It's like this. It's not Gaussian. It's some Gaussian but minus some delta function. So you can imagine it's you can see it's some head but upside down. So if you put the original your images, you apply this Laplacian of Gaussian filter just to do the convolution, you have something in the middle. So where the highest intensity or value gives you some like central position for each particle, right? And then you just use some Schrodinger method. You can find or some fitting method. You can find the central of each bead. So for example, on the right hand side, that's the detected position of the central of each particle. This method is very robust. You can, if you add more like a portion noise or torsion noise, it can still give you very good measurement of the central position of each particle or bead. It's not only for just like this fluorescent beads, even for those cells, it still gives you something for the central of the cell. And besides the LOG, this Laplacian of Gaussian filter method, I've also introduced the deconvolution method. The point spread function based deconvolution method. So firstly, what's called the point spread function. So basically to describe the response of the image system to a point source or point object. So for example, you have some object, that's your ideal fluorescent particle bead, right? But because you are using some imaging system, like a microscope, right? So there's some point spread function have been applied, it's convoluted. So finally, you have your images. It actually look like some blurred some images. So that if you just directly to measure the centroid of the final image, like there may be large area there. So one idea is if you know the PSF function, you should do the deconvolution first to give you a better what's the real object should look like, and then you find the centroid of the object. Object means the fluorescent bead. And to find the PSF function, there are many ways. So one thing that you can just if you know everything, all the physical setup of your microscope, you can know what's the PSF function, or just use the definition, the point spread function. So in your images, maybe some particles they may affect the other particles, right? But at least you may find some particle is far away from all the other neighbor particles, and you know how it looks like. So this can be directly used as your point spread function. So find those point spread function, do the deconvolution. You will better get what's the object image rather than use the raw image. So here's one of those examples. So for example, on the left is what's your microscope images. So there are particles there, right? But if two particles they are very close, or they may be blurred, so and they may have some, because their blurred images may have some overlapped area, right? So this will affect how do you detect the centroid of the particle. So what you can do is for this whole field, you just find one particle or two particles of those either far away from all the other neighbor particles, right? Use the definition with the point spread function, find the point spread function, and apply the deconvolution. So the deconvolution image, you can see the particle, the radius is much smaller than the particle in the image on the original image. So use this deconvoluted image, you can better find what's the central position for the particles. And then use this position to apply the particle matching or leading part. So on the right hand side, that's the results where the image has been deconvoluted. You can see for each of these particles, the radius is much smaller compared to the left ones. Oh, there are many other methods, like you can do some machine learning method to apply just for the time limit, just to introduce these two popular, but they are already robust and they are enough to handle most of the cases. Okay, so this will be, we'll just combine all the demo and the this theory together. So next I would demo you how do we detect the 2D and the 3D particles. So I just wonder if do you guys just want I just show you everything, or we can give you like 5 minutes, or so you can also try by yourself. So I prefer the latter, so everyone agree, right? Okay, so if that's true, so first I hope I will put these 2 links on the channel. I hope you can download this data sets and this code, and we will do this together. So first, to detect the 2D particle, I provide you both the MATLAB app, you can also use the scripts to find where the particles they are for the 2D particle and for the 3D particles. And after this part, we move to the matching or linking part. Okay. So before so first I will copy this to, so it's the same box folder with the yesterday's box, some subfolders of yesterday's folders. I will copy paste these links to the channel, tech channel. Yes, it's already in the chat channel, so you can download these 2 folders, one the code, one data sets. The code looks like this. So I just either link does the link work for everyone?
Hey, Jen, yeah, I was able to open both links, but the first link says no atoms in the folder. The folder name TPT. I saw 3 subfolders in the TPT underscore code folder. Yeah, I saw. I'm seeing this one.
So you are missing the data sets one.
Yeah, this one is empty.
I got it. Oh, Jane, I think that's fine because I already put some data sets in this TPT code.
Okay.
Yeah,
good.
so just download these 2 codes. There's already data sets there.
Okay. Yeah.
Yeah. So after you're downloading, I hope you can open your MATLAB and let's first go to the LTPT2 code to detect those 2D particles. And in this example, I will show you one is the simple but the synthetic image. So everything that very ideal case, right? And then I will show you one of those experimental images. So there are 2 subfolders starting from IMG image. So one is the synthetic images. If you can open them, they are the just some dot pattern. And then in the other image folder, that's some pipe folder. So this is the flow, the pipe flow. So because there's flow in the pipe, so many particles they're also in the pipe and they flow. And because there's some deformation, right? So more than 1 frames are recorded. So if you compare the first frame with other frames, you can know what the deformation is. So if this works for everyone, so there's one M file called just under the path, the LTPT2 code. There's one just called mean TPT training detection. So we can open that file.
I need a bit time for downloading. It's still continuing.
Okay.
It's 1.2 gigabytes, the whole folder, I guess.
Okay. So now why not? Let's just wait till you download the app. Finally, I will give you some time after this step that I can show you how it looks like. Yeah.
Okay.
Because it's quite easy just to open this folder, open this new file, and then run this file. And there's some parameter you can just change, adjust by yourself. So first is just run first section to add the function to your path, and just run this app. You can just run this line, or just click the app and then run it. So first, let's demo the 2D case, right? So you just choose the 2D and choose the harder particle, and you can choose the cumulative mode. The 2D, 3D is just either 2D particle or 3D particles. The soft hard means do we consider the shape change of the particle? Because I think for fluorescent beads, you can always use the harder particles. But you just imagine you print something on the surface of the foam, right? So with the foam, with the compression a lot, the particle shape will change from spherical to some elliptical shape, right? So you need to consider those shape change as well. So that's why there's the soft or hard particle. Cumulative mode or incremental mode is the means of cumulative mode is the more happening for the solid mechanics. You are always compare with the first image with the undeformed configuration. Incremental is that you already compare two neighboring frames, right? So it's more cumulative is more useful to compute the final result displacement strain. The incremental is more popular. You can compute the velocity field. So after you run this, just click the next. And another app will just show up. So here we use the same, lots of those same functions with the LDIC and LDVC function. Either you need to load your images. If you have mask file, you need to select mask file and choose the particle detection method. So here first, I will show you the synthetic one. So there is no mask file. And you can try TPT or Laplace of Gaussian filter by yourself. Oh, and there are 4 parameters you need to define. So if I load the image, so you just to find those folder you want to load. So for example, here I just find this image translation hard particle. So they the hard particle, they have the rigid body translations. I just load this particle. And it lets me to define what's the region of interest for this analysis, right? So I can define a region by clicking the top left and the bottom right corner points. If I want the whole image to compute, I can compute the very outside the left top corner and the bottom right corner. So after you select the 2 corner points, the image will show on the right bottom. So there are lots of thresholds you need to define. For the bit size, this is just the estimate of the bit size. And the mean size and the maximum size, that's the lower bound and the upper bound. You can further to zoom in your image to see what's the some lower bound and upper bound for your bits. Because some bits, they may not have the uniform size, right? So if you apply some bounds, it will help you to remove those wrong detection. Threshold is just because the particle tracking, you need to define lots of those bit parameter. Different parameter will give you different results. So I will run this first. That's how it will look like. So that's the track. That's the detected particles. You can always to further zoom in each window to see how it's always that you may miss some particle, but you can detect most of these particles, and you can just adjust these values. It will give you different results. And the bottom is how many particles are detected. And so, Sina, maybe other people have the same question. They are still downloading your code, right? So I will give you some time to run the code, but before that, I will just show you sometimes you may don't want to use some app, right? Because it's hard to change the values. You can also use the scripts here. So the scripts is just to do the repeated work. I just do this through the app, so the same thing. So first is to load the images and then to define those parameters. So instead of buying this box, so here just to put those numbers, use the scripts, use these lines, and then run the code, and finally you will plot what you detected. So I just give a quick demo of this. So if I just run this from the beginning, I just do the same thing. I choose the folder where the images I want to analyze, right? And then I define the region of interest by clicking two corner points. You can see these are all the detected particles. And another one function I want to introduce before you start your demo is sometimes just like these pipe images is you may have some region, like for example, this is a pipe, right? So what you only want to analyze is the bottom part. You don't want to analyze the very top left or maybe here some some particle there. So if you want to remove these regions, right, because this may affect your overall particle tracking algorithm. So one thing that you can add a mask file. So mask file is the same size with the image size, but it only have 0 and 1 binary number. 0 means no, 1 means yes, which means 1 will be used. So for example, in the pipe folder, there is a one mat file called the image ROI. If you look at those images, the size of each image is 800 by, there's some inverse size, but they have the same size for the image ROI. So this is some mask file of the images. So you can further to select this mask file or define your mask file by changing this to your mat file, the path of the mat file. So for example, if you use the app, so if I use the app, I choose the 2D hard particle cumulative mode. I click next. So now I still select the image folder, but I have the mask file. So I can, when I load my image, so here I choose my pipe folder. I define a region of interest. Again, I can to load my mask file. Again, I can just run detection. You can see all the, because the mask file, this example I also choose the ROI to the other part, but the mask file is already enough, so you can only detect particle at the bottom. Just as similar as before, you can see these particles, they are not ideal spherical shape, right? But you may miss some particle, but you can track most of them. Okay, so next is a few minutes is your time. So Julie and Cindy, have you finished downloading the code?
Yes, I'm okay.
Okay, it's okay. So I hope you can open this ALTPT2 code first, unzip it, open it, and try this 2D particle detection first. And I will give everyone about, if you just run this M file, maybe 5 to 10 minutes. If a question, just you can leave message or just speak out, or maybe use the chat channel. Alex, did you see the app or did you mention the code, the script?
I use a script, but it's always busy. So
Are you marrying the pipe or marrying the synthetic hard particle?
the synthetical.
I see.
Just-
So if you don't mind it, because here already the 40 images there, you can delete maybe 30 or 35 of them.
Okay.
Usually 2D is super fast. Like the computer I showed you is not that powerful. The RAM is only 16 gigabytes, so it's okay, but it's not that powerful. So you should have similar speed.
Should we select a parallel computing?
Oh yeah, if that's possible, that would be better. So here you can still see my screen, right?
Yes.
Okay. So open your parallel computing setup. If you go to your MATLAB, the top, the menu, you can see there's the parallel option,
Right.
and there's the parallel preferences.
Right.
And they change the preferred number of workers. I don't know how many cores you have. I think maybe you the default one, maybe 48 in the. If you choose the number is larger than your physical cores, it will just decrease number to the real ones that are available.
Okay.
Let me try again.
Yeah, I'll try that.
What is the log code and TPT code? What are they standing for?
Say again, what's the local TPT code?
Yeah, there are two options, log code and TPT code. I think we are working on log code right now. What are they standing for?
Local TPT?
In the particle detection methods on the app, method 1 TPT code, method 2 log code.
In the app or in the?
Yeah. What are they standing for? Method 1 TPT code and method 2 log code.
Oh yeah. So if do you remember I just introduced the two detection method? One use the deconvolution, one use the Laplacian Gaussian.
Yeah, I recognize.
Yeah. So TPT means here we use some deconvolution, and LOG means we use some Laplacian Gaussian.
I see. Okay, thank you.
So why use the deconvolution to shrink the particle size, right? So you can better detect the centroid position of the bead. Why they use the Laplacian Gaussian? It's kind of like the second derivative to find the peak of the particle.
I see. Thank you.
Yeah. The safety I haven't implemented yet. For the particle detection, actually, there are tons of those, many methods there available. So Alex, did your code run or okay or still busy?
Sorry, let me try. Still working on it.
Oh. Does anyone have other issue for this part?
I have a question.
Sure.
When I open the NPT detection app, there's an arrow in trial NPT detection /load image button pushed, and I'm not able to load the image.
Do you mind just trying the script one? So
Oh, okay.
if you have question, you can. I will stay longer after this session. It's just yeah. So that I can help you share your. I can let you share your screen and I help you debug. But I hope with everyone just at least one script or app, one of those methods work, and then we can just keep going. Oh, I could ask, what are we doing after detecting particles? Okay, so after we detecting those particles, right? So we will matching the particles to find the displacement field. Yeah. So all the tracked particle is stored in the particle coordinates. So for the particle detection for now, we only detect a particle on one frame. So you only have one particle coordinate A, and the row number is how many particle have been detected, and the column number is the X position and Y position. The other one need longer time. So I hope like you may see something like this, where the particle has to be detected. Yeah, so if everyone have no question, so we will go to detect the 3D particles. So what you just did is to detect the 2D particles, and then we'll move to 3D. So 3D, there's another code called LTPT3. Open that folder. So again, similar with before, there's the app and there's the script. I would suggest that everyone run the script first because of the time limit, because app may cost longer time. And here, so for the script, you need to choose what's the file name for all your Mac files and what's the path for where these files they are stored. So for example, I have uploaded two folder for the images. One is the synthetic images, one is the experimental images. They are already in Mac files. If you want to see them, so for example, in one of those, you can click it, and you can use the function image ESA3 and the volume 1 to see how it looks like. So this is how it looks like. And you need to modify the file name for all and the file folder for these images. So if I choose the hydrogel indentation experimental data sets, so the folder is the file name is called volume VOL 2019 May 4th, and then is the star.mat, and the file folder is the /line image hydrogel IND. And then just similar to before, there's the TPT code and the log LOG, Laplacian Gaussian method, and there's a threshold you can train. Also have the bit size, minimum size, maximum size. And just to run this code, you can find where the particles are. And and in this images, because it's three-dimensional. So because it's 724 by 74 by 306. So I just select at one of those frame number with some weight to overlay the detected particle with the original image to show you how they look like. So if you open this min file in the ALTBT3 code, just modify to double check the file name and the file folder that's correct. Just run this file. So I will wait for you running this, but finally you will have two results. So one is the other particle that has been detected, so the 3D, because there are so many particles there, so it looks horrible. One is at one of those frames. So here I choose the 31 frame, and with some length, with some width 3. So I show the frame at 31, so that's a 2D image. To plot all the detected particle between the 28 to 34 for the stack number, and overlay with the 31 2D image to show you how good the detection are. So because you can see there are many parameters you need to adjust when you have very good detection. So just simply running this can give you like a good choice what the particle parameters are. Okay, so now it's your time. Yeah, I really appreciate if someone you got the same results with mine. Just you can share this this news with me that you have finished this part.
Hi, Jin. Just ask you, how can you visualize the displacement?
How do I want reload?
No, how do you visualize a displacement for each particle?
Do you mean the location or displacement?
Oh yeah, so displacement. If you have a location, you can calculate displacement, right?
Yes. So that's the same with Echo's question. So for this step, we all need to get the location, right? So if everyone works okay with this part, I will share how do we for the particle matching. So for example, for the reference image, you find all the particle position, right? And for the deformed image, you find another particle position, right?
Right.
So next important step is to link the particles. So same particle in the same particle from the reference image and the same particle from the deformed image, right?
Okay,
And then you just minus the location in the deformed image minus the location in the reference image, you get the displacements. And with the displacements, you can get all other information like a strain, velocity, like all other information.
So your code is only for detection, right?
I have something to show you after that. But first this part is detection.
Okay.
Yeah, because I don't want to make everything misunderstanding or like a messy, because the code can be super long.
Right.
And so these two code I just mentioned, the training detection part is only for detection. So
Right. Yeah.
yeah, so this can help because even this particle detection, you can see there's already many parameters there. So I just want, so in your real experiment, sometimes you may need to train these values, right? Like what's your threshold? What's the bit size? What's the maximum size? You need to train these values. I don't want to mess around all the things. And I don't want to confuse people either. This is the volumetric image. So here, actually the 3D, what I showed you just near around one slice, you can change the slice number. But if I change to 100 slice, I can still plot the bits near that 100 slice now to check how accurate they are detected.
Okay.
So why I say you need to train these values, because just like I said it before, it also depends on experiments. Right? Just like when you do the experimental design, if your particle size is too small, just like one voxel, it's hard to distinguish it's a real particle or it's a noise. Right? If the particle is too big, so you lose some spatial resolution for your measurements. Right? Similarly, for the here threshold, for example, the same thing. If this threshold is too small, if you may add lots of noise also to take the noise at the particles. But if you choose the threshold too huge, like 100%, for example, you may also lose many particles as well. So this needs users' experience and to consistent with your experimental design of the particle. Okay, so I could let me to demo 3D detection again, file name change. So the only thing for the file name change you need to change is around the line 40 to 41 to 42. So file name all, that's the prefix of the file name for your 3D images. So if you use the image hydrogel indentation, it will should be named by volume VOL something before the 01 and 02. So use the star. And the file folder, because it's a subfolder in this ALTPT3 code. So use the dot and then slash line and the image hydrogel in the IND. That's the name for this subfolder. So if you choose the synthetic hard particle tool, so you should you can see you have different name, right? Because now name will be VOL short line 1 star dot mat, right? And the similar file folder will be where the folder it is. Echo, did this answer your question?
Yes, I got it. Thank you.
Oh, you're welcome. Is there anyone finished this part for the particle detection? you can just raise your hand or maybe give a message or say something. Oh, just by the way, just a quick comment is if your experimental setup is always the same, right? So you can use the same parameter for all the frames, right? So but sometimes if your experimental condition changes, right, you may need a different parameter for different frames, and you need to check the particle are detected correctly. Okay, and then we'll move to the next part. So if a question, I will stay longer, so you can still ask me. Okay, next part is the most exciting part. Is the so now we detect those particles for 2D particle and the 3D particles. Yeah, you can try by yourself later on. 3D, there's also app you can try. But this is super slow compared with the script, so I would recommend use scripts. Also, 3D, there's the slide bar you can shape. So this sometimes is more expensive.
Jin, sorry, could you please go back in the 3D particle detection slide?
Sure.
Yeah, we have a detected particles in layers, and down at the downside we have a figure. What does it show? It shows through the z-axis.
Yes.
Okay, I see. So it increases as we increase the layers. It goes down and down, right?
So either from the first layer to the first z stack to the maximum, you know, the top of the z layer. Oh, I'm guessing I understand the question. Are you asking? So this is the same thing.
What is the image showing us? The image below, yeah.
Yeah, the image below showing is the same. You use the script. Either you just find one layer number, you define a thickness. So you overlay this 2D image with the, you know, for example, this one, the 80, right?
This is the 80th layer?
Yeah, this is the 80th layer.
I see.
And the particles are detected within 80 minus 5 and 80 plus 5.
Oh, okay, I see.
Yeah.
So into the 3D image shows us the 80 plus 5 and minus 5, and this single image shows the 80th layer.
Yes.
Am I correct?
Yes.
Okay.
Yes.
Thank you.
You can change data values. Yes.
Thank you.
So it's the same what you did use the script.
Yeah, I see. Okay.
Yeah. That's good. Thanks. Okay, next part is the particle matching. So this is exciting because you find a lot of those particles in the reference. You can detect particles, right? So now you need to link in them. The thing is that because you can detect a particle in the reference image, and you will detect some particle in the deformed image, right? Because the sample have some deformation, so particle position will also change. So the thing that you need to find which particle goes to where, and then you can just subtract the location and find the displacement. So you need the particle link and find the corresponding particle. So there are many methods I will introduce here. So first I will introduce the Mohawk's, my groupmate Mohawk's paper is the topology-based feature for the single particle. So what he did is this. So you find one individual particle, and you find all the, for example, all the 20 neighbors of this particle. So you find the 20 neighbors of this particle, and based on the quadrants. So in the 2D, you have 4 quadrants, right? And in the 3D, you have 8 of those quadrants. So you can rewrite the and based on the area. So you can for example, radius 1 and radius 2, right? So you can cut the neighbor into those 8 regions. So for 2D, 8 regions. And you count the number of particles within that region. And you rewrite this based on the same order, rewrite this into a long row vector. And this row vector is one feature descriptor of the particle. And this descriptor is just to written by the its relative position with the particle and its neighbors. And then it's just by minimizing the distance between the different those feature descriptor vectors, you can find which particles to where, and then you find in the particle linking. So let's imagine this. For example, you have one particle looks like this, right? And you shift something, but the relative position with your neighbors are fixed, right? So the same particle, even you have some translation, but the feature descriptor is the same, right? And if you compare the feature descriptor, you will find the corresponding particle. And then you find the particle matching. So is this part clear for everyone? So imagine if just a translation, like no rotation, no shear, so this will work, right? And so people may ask because it's a simple idea, right? And it's effective. So what if there's some rotation or shear? So what if some particle across this x-axis or y-axis? If this method is still accurate. So to do this, there are two strategies have been applied. The first strategy is so for example, for this 2D case, so for each particle, for the number of its neighbors, right? Because it's 2 circles and each circle had 4 quadrants. So totally for the feature vector, there's 8 numbers. So firstly, for the linking or matching, we don't need to let all the 8 numbers be the same. We can only let, like, for example, 12-5 or 12-6 to be the same. So give it some flexibility to allow some error. And the second thing is there's a method called iterative deformation warping. The idea is this: so some particles, they may have some like a distortion or rotation, right? But you always have someone that's good in the definition is small. So you first use those particles to get some initial guess of the deformation field. And then you just use this initial deformation field to warp the image. And then you apply this image detection, matching, and the deformation warping just iteratively. So finally, you can always get a good one. So for example, here is one of those examples. In the first iteration, maybe only one of those, where deformation is small, you can correctly link. All the others, because there may be some rotation, means something, they are not linked. But with this initial guess, you can already to interpolate or exclude some definite field. And then you can warp the image or warp the position of the particles. And then just re-mirror the descriptor. And then just to match, you have better for the topology relation with your neighboring particles, right? And you can increase the ratio for the matching ratio. And you do this iteratively, you finally find the final iteration. I don't know I explained this clear or not. So you can imagine this is some feature descriptor of your neighbors, right? So maybe this feature is not that intuitive. So here's another one is so for example, you can for each particle, you can find all your neighbors, like first 20 neighbors. And you can measure the distance between the particle, central particle with its neighbors, right? And with this distance, you can plot some histogram. So because the particle, they are random, but they are not accurate square pattern. So there's some randomness, but they are unique. So if you plot the histogram of the distance between the particle to its neighbors, you will have some possibility or some histogram plot. So when particle have some deformation, it's moving, but the relative position to its neighbors still keep those topology. It's just like stars, like star constellation. They are always moving on the sky, but their relative position to its neighbors is kind of like have some fixed topology relations. So you can still to find the corresponding particle. So here, similarly, for example, you can still use this histogram of the distance to your neighbors and finding which particles to where, because each particle has the individual feature for this histogram descriptor. Besides this histogram, you can also use the angle and the distance, those polar coordinates relations. So there are many ways to define those topology features. You just the histogram, or this 8 quadrants, or this angle distance polar coordinates. So there are many ways. Here's the 3 of those methods. But once you define those point feature descriptor, you can to find the linking between the different points, and then you match them and find the displaced field. Yeah, here the advanced topic is sometimes you can also do the multi-scale way that you have two different color or two different types of fluorescent beads. You can use one type in the sparsely distributed, measure the one definition first. That's your initial guess, and then further to refine to a second type of the fluorescent beads to increase accuracy. So there's some multi-graded method as well. I think we can just try one example, and then you will know what I say. So here's the example from the experimental data sets. It's a hydrogel and indentation. So if you open the method code, the download. So there's another one called TPT GitHub. So in the TPT code, there's another one called the TPT GitHub. So this is Mohawk's published results use the his topology-based feature to match or link the particles. So here I already added the data sets, the image hydrogel in, and there's the code, and there's the example run file. So firstly, you need to guarantee the code is already on your path. So you can just right click the code subfolder to add to path, and then open the example run file. I also put the Mohawk's paper in the same box folder, so you can check his paper. So here so I will show you this and then give you time to run it by yourself. So here what to define, the first to define what's the name for this meta files. Again, this meta file is the same as before. So each meta file is a 3-dimensional data set. So this image has the 1025 in the X dimension, 1025 in the Y dimension, and the 306 Z stacks, and the 16-bit images. So again, you can use the figure image SC to plot it. So this is the reference image. So this is so here the X, Y, and this slide bar is the Z direction. You can also change the dimension by clicking the view, point of view. You can see there's a different point of view. So if you also click the cut 02, you can plot another figure. So that's a different one. So even before you do the post-processing, you can still see there's some indentation. I think you can see there's some indentation because there's the steel bead there. So some particle have some concentration near the the boundary between the feed and the bottom hydrogen. So you can also plot the other direction. You can see there's some feed indentation. Okay. So same again here, you need to change the name for these files to add these. Yeah. So before you run, you don't have this result file. Yeah, you don't have these volumetric data files. So in Mohawk's code, he assumed everyone already know what's the good bit parameter. So that's why I just showed you how to. There's the tool, you can try different parameters so you can know which one works better for your case, right? So assume you already run that detection part, you already know what's the best parameters for the bit detection. So now just plug in those. TPT parameter had 2 of those. Most of them need 2 of those. Either for that 8 quadrants. In 3D, you have 1 sphere, you have 8 quadrants. But 2 sphere, you have 16. You want the 2 of 5 are the same, and then just run this example run file, and then you can get a definition field. So I just run it.
Yeah, I also clicked run. I got the same error as you.
Yeah, let me see what happens because I just do. Thanks, Jim. Yeah, because this I just downloaded from Mohawk's GitHub, the Frank Lab GitHub. Well, I think I don't know why, but looks like now it works in the tool. Just put everything to the main file. Like don't use the image folder. You can keep the code. You can keep the code. You can still keep all the code. You can still keep all the code. Don't change those. But put all the images to the outside. So put these 2 images outside. Yeah, then on my computer it will run 5 minutes. So I hope everyone you can start running this part. Oh, Jin, does it work now?
Yeah, it's running.
Okay.
Could you please repeat what should we do?
What you should do is put the images to the outside of the subfolder.
Okay.
Yeah. I think Mohawk assume you should put the volumetric data file outside, the same path for the example run file. If you run this, you will see those iteration steps message on the MATLAB command window. So it will tell you which iteration step it is, what's the time cost for that step, and how much percent for the particles are tracked, and what's the current subset size.
Hey, Jin, I have a question. Can you explain what is the two mat file you just moved?
Oh, so yeah, so what you should do is to put the mat file from the subfolder to the main path.
Yeah,
Yeah, that's it.
I mean, what are those mat file?
So where are these mat file come from, right?
Yeah,
Okay. That's a good question. So I should explain more because it's one I cannot show you now. But this mat file actually is if you look at the size for this mat file, it's a three-dimensional matrix, right?
yeah,
So this is what your images. So like no matter microscope or other imaging tools, what you get is these images, right? So imagine you have these stacks of those images. So here, each of these stack is the size of the 1024 by 1024, and you totally have 306 these stacks.
okay, so 0, 1, and 0, 2 are just timestamp. Right? Just
Exactly, yes.
okay. But how does this relate to your previous detection code?
Okay,
Ah.
so in this example run file, right? So here you can see the bit parameter that defined here, right?
Yeah, so previously what we run cannot the same algorithm for detection.
So previously you only do the detection, so where you can change this parameter to find the best parameter in your case.
Oh, okay.
Because this example run file, there's no simple way to tune this parameter before you're running the code.
Okay, so the first step is to find a correct parameter by your code.
Exactly.
And
Yes.
then run his code to get the tracking particles.
Yeah, actually
Okay.
his code in the published just this part. I just write a new code to help you to before running this code.
Okay, cool.
Yeah.
Actually, it's easy to get these mat files. Just save the first channel of your grayscale value of your image to the mat file. It's how you get it. For
Oh, that's
example,
great. That's great.
it's easy.
Jay. Thank you, Jay. I will also I can upload one code now where you can transform. Imagine you have some TIFF file or some other image format. You can also transform those go to these mat files. I hope that will help.
If you open the mat file and just image use content, you can see that it's image actually.
Sure. Yeah. Oh yeah. I finally after about 5 minutes, I got a displacement field. Yeah, with this displacement, if you look at the code, finally you have the X and the U, right? So you can further to get the strain field and compute the traction or stress.
I got this, Jen. I got this too.
Oh, that's great. Thanks.
Got it too.
You got it? So
I have a question.
Yeah, go ahead.
Yeah, so I'm getting this error message where it says my output arguments are not being assigned during call to fund TPT, and I'm not sure how to fix that.
Either error message long or short. If the short, you mind sharing to the chat channel.
Oh yeah, I can just.
Yeah. So
You had to move the outside.
I think I already moved it outside. Yeah, because
This is the example round 5.
Oh yeah,
Uh,
Echo. To put this mat file from the image hydrogel in to the min path.
Yeah, I think it's out there.
It's out there, and you run this example file, then you still see this one message, right?
Yeah, so my the two map file that you asked us to move are in the same path as the example run file now.
Do you mind just waiting for 2 minutes? So I just finish some final announcement, and then I can help. That I
Oh,
can
yes,
allow
of
you to
course.
share the screen. Yeah,
Yeah, absolutely.
because of what? Yeah, thank you. Thank you, Echo. We run out of time. It's almost so. Just finally, I just a quick summary. We have lots of collaborator and people users help us develop code. Right? So if you have some good idea, feel free to share with me, and all the videos will be recorded and uploaded afterwards. And if you want to we have lots of advanced tools because the time limit. So these two sessions only cover part of it. If you have some personal or some customer needs, you can just ask us. And feel free to leave if you have other meetings. I will stay like 1 hour, half an hour to 1 hour. So if you still have questions. Thank you all. Echo, I can let you as the.
Oh yes, that'd be great. I can. So I have these two map files out here, and if I hit run, it's still the same error message.
Oh, I see where the let me see. I see where the problem. So in your line 115.
115.
Yeah. So the file name should be change your 01 to a star.
The star.
Yeah.
Oh, like
So
this.
yeah. So the explanation is if you just write at 01, it just choose that exact one file. If you choose a star, it will select both two files, naming starting those things before the star.
Oh, okay. So and it requires both of the files too.
Yes.
Okay.
Yeah.
Sounds good. Thank you.
Yeah. Welcome.